got another short little version of this here. For whatever reason, I had a little technical difficulties, and we're going to have to finish this up again. But the first one I want to go over here, question 31, says a barg magnet with north and south poles marked on it into three pieces in such a way that one of the particles does not have any pole marked on it. How can its polarity be determined without using a new bar? Well, I want you to remember what the Earth, all right, the Earth, use green to represent the Earth, the Earth has its own poles. And it's just the opposite of what we would have thought of maybe a month ago. But the North Pole is the magnetic North Pole is actually towards what we call the South Pole. And in here then, there is this field that goes from north to south. So let's say I take a magnet, this broken magnet, and I stick it here in the middle of this. All right, I take this magnet and I stick it here in there. Well, it's going to naturally turn itself and twist itself so that its magnetic north is pointing towards the North Pole or the magnetic South Pole, and its magnetic south end is going to align itself automatically with the Earth's magnetic north. And that would be an easy way for you to be able to identify. Almost treat each piece like it's an individual compass. Put it somewhere so that it can spin how it wants to go, maybe on top of a needle, maybe if you can get it to float on the top of water using the tension in water. Those would all be ways. 32. What happens to the polarity of an electromagnet when the direction of the current passing through it is reversed? Well, let's look at a wire, and I've got the current here. And in this wire, we're going to have the current. If I use the right hand rule and point my right thumb up with the current, my fingers are going to wrap around. And what that tells us then is the direction of the magnetic field. So what happens, kind of looks like the Colts, unfortunately, they lost yesterday. What happens then if the current changes? Well, let's say the current now changes direction and the current starts heading down. Well, my right hand rule, which I'd have to use, it's going to change as well. Now my thumb's going to go down and my fingers would wrap around the backside. So what would happen here is the field would be changing direction because the current changed direction. So what I want you to understand is if we change the current, then the field is going to change direction as well. So if the current changes direction, the field will change direction. If you hold a bar magnet in each hand and bring your hands together, will the force be attractive or repulsive? Well, we've got two examples here. One where we try to bring two north poles together. The fields in both cases are going to be coming out of the north. And what you'll see here is this repulsive force. They're going to be repulsed by each other. The other case then is if I brought a north pole and a south pole together. The field is going to go directly from north to south, and that's going to attract them to each other. The last one here asks about whether or not a magnetic field is real, or is it just a means of scientific modeling. The field is very, very, very real. The field is there. That's why all of the little demonstrations, everything we've done, we've been able to find out that the field is indeed there, whether we can see it or not. For example, one of the labs you did is you held a compass around a wire once you had current flowing through it. The compass was getting caught in the field. Now the lines aren't really there, but the field is. That compass showed us that the field is there. The lines are just drawn there for the scientific modeling. So the field is real. The lines are just the scientific modeling. Hey, I hope this helps you. I'll see you on the flip side.